Hello and welcome to Chapter 9, Section 1, Sequences and Series. A sequence means a listing of numbers or expressions that are ordered so that it has a first member, a second member, a third member, and so on. A sequence can go on forever or have a certain number of terms. An infinite sequence is a function whose domain is the set of positive integers. The function values a sub 1, a sub 2, a sub 3, a sub 4, so on to a sub n, and on to infinity, are the terms of the sequence. If the domain of the function consists of the first n positive integers, only the sequence is a finite sequence. Write the first four terms of the sequence given by a sub n equals 3n minus 2. So I'm looking for a sub 1, a sub 2, a sub 3, and a sub 4. So that means I just plug in the sub number n for n. So I'm looking for a sub 1, which is equal to 3 times 1 minus 2, which is 1. Then I'm looking for a sub 2, which is equal to 3 times 2 minus 2, which is 4. Then I'm looking for a sub 3, which is equal to 3 times 3 minus 2, which is 7. And then the last one I'm looking for, a sub 4, which is equal to 3 times 4 minus 2, which is 10. Okay, now we want to do the first four terms of the sequence given by a sub n is equal to 3 plus negative 1 to the n power. So this time the numbers are going to go in as an exponent. So that's going to be a sub 1 equals 3 plus negative 1 to the first power. And that's going to be 2. Next one is a sub 2 is equal to 3 times negative 1 to the second power. Well, that makes that negative 1 positive, so my answer is, oops, I'm sorry, that's a plus in there, plus, so that makes that 4. And next we have a sub 3 equals 3 plus negative 1 to the third power. Well, that makes negative 1 negative, so that's going to be 2 again. And if I do a sub 4, that's going to be equal to 3 plus negative 1 to the fourth power, which is going to give me 4 again. We notice that these go back and forth, 2, 4, 2, 4. Whenever it's an odd term, it's 2. Wherever it's an even term, it's 4. Okay, now we're going to come up with the expression for the nth term, a sub n, of each sequence. So let's say a sub n equals, and we see we go from 1 to 3 to 5 to 7. There's a difference of 2, so let's do 2n. Okay, now if I do a sub 1, that's going to give me 2 times 1, which is 2. But I need 1. Well, that means I'd have to subtract 1 from that to get that. Well, let's see if that works. Let's say a sub 2 equals 2 times 2 minus 1 equals 3. So far, so good. Let's try another one. A sub 3 equals 2 times 3 minus 1 equals 5. And it seems to work. So we're going to say that my expression is a sub n is equal to 2n minus 1. And there's my expression for a sub n. Okay, on the next one, we've got fractions. And as we're looking, the fractions are getting smaller and smaller. And if I look, okay, there's 1/2. And then there's 1/4, 1/8. The bottoms are going up by a value of 2. So let's see. A sub n equals, well, I notice, like I said, 1/2. Well, if I can get that first term to be a 0, 1/2 to the 0 power will give me 1. So that's 1/2 to the n minus 1. Let's see if that works. So a sub 1 gives me 1/2 equals 1 minus 1, which is 0, so that's 1/2 to the 0 power, which we know is 1. Let's try a sub 2. 1/2 to the 2 minus 1, that's equal to 1/2 to the first power, which is equal to 1/2. A sub 3, that's 1/2 to the third power, which is equal to 1/2 to the third, or 3 minus 1, excuse me, so that's 1/2 to the second power, which is equal to 1/4. And those numbers all fit, so then we did come up with the correct expression, a sub n equals 1/2 n minus 1. Sometimes there's going to be some trial and error when you try these problems. Next, we're going to look at factorials. And if n is a positive integer, n factorial is defined as n factorial equals 1 times 2 times 3 times 4 times all the way up to n minus 1, and then times n. As a special case, 0 factorial is defined as 0 factorial equals 1. Okay, let's evaluate each factorial expression. The first one is pretty cut and dry. It's just going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. When you multiply all that out, that becomes 3,628,800. Okay, now let's look at another one, but this time let's see if we can simplify it before we come up with an answer. Okay, 2 factorial we know is 1 times 2 times 6 factorial, 1 times 2 times 3 times 4 times 5 times 6. Okay, and that's over 3 factorial, which is 1 times 2 times 3, and 5 factorial, which is 1 times 2 times 3 times 4 times 5 times 6. Oops, I'm sorry, 1 too many there. It's not times 6, just a times 5. Okay, now we can start getting rid of things that are alike in the numerator and the denominator. Those go away, 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 those go away. So on the top, I'm left with a 6. On the bottom, I'm left with a 3, which 6 over 3 is 2. Now that was pretty easy. Now let's look at the next one because it doesn't have any number values. We have to figure out what it is with n. Okay, if we remember from up there at the definition, we know n factorial is really n minus 1 factorial times n. Oops, not n factorial, just n. Over n minus 1 factorial. The n minus 1 factorials divide out, leave me with an answer of just n. You will need to copy this down. This is the properties of sum, so pause the video at this time and copy these down. There is a convenient notation for the sum of the terms of a finite sequence. It is called a summation notation or sigma notation because it uses the uppercase Greek letter sigma, written as sigma. Definition of the first n terms of a sequence is represented by I equals 1 to n of a sub I, which equals a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus ... plus a sub n, where I is called the index of summation and n is the upper limit of the summation. and 1 is the lower limit of the summation. Okay, let's do a couple of summations. We want to find the sum of each, so that means that I'm going to put in 1 for I, then 2, then 3, then 4, then 5. So that's 3 plus 3 times 2 is 6, plus 3 times 3 is 9, plus 3 times 4 is 12, plus 3 times 5 is 15. Okay, all we have to do is add them all up, and my answer is 45. Okay, we're going to do the same thing with the next one, except for we're doing factorials, but this time we're going from 0 to 5, so that's 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial. Okay, all we need to do is simplify. Well, we know 0 factorial is 1, so that's 1 over 1 plus 1 factorial is 1, so that's 1 over 1 plus 2 factorial is 2, so that's 1 over 2 plus 3 factorial is 6, so that's 1 over 6 plus 4 factorial is 24, so that's 1 over 24 plus 5 factorial is 120, so that's 1 over 120. That means my common denominator is going to be 120. So I've got 120 plus 120 plus 60 plus 20 plus 5 plus 1, which comes out to be 326 over 120, which we simplify that down to 163 over 60. Okay, definition of a series. Consider the infinite sequence a sub 1, a sub 2, a sub 3, a sub I, and so on. The sum of the first n terms of the sequence is called a finite series of the nth partial sum of the sequence. And it's written as I equals 1 to n of a sub I, which means I'm only doing the n first terms. The sum of all terms of an infinite sequence is called an infinite series and is written as I equals 1 to infinity. And that would be a sub I is equal to 1, and it goes on to infinity. Okay, you might want to write down the properties of sums. They're on page 647. Okay, we want to find the third partial sum of the series. So we do 3 over 10 to the first plus 3 over 10 to the second plus 3 over 10 to the third. And that's equal to 0.3 plus 0.03 plus 0.003. Or my final answer would be 0.333. Okay, now we want to find the sum of k equals 0 to 4 of 5 over 10 to the k. So that's going to be 5 over 10 to the first plus 5 over 10 to the second plus 5 over 10 to the third plus 5 over 10 to the fourth. Okay, that's going to be 0.5 plus 0.05 plus 0.005 plus 0.0005. Okay, so we add that all up, and that's equal to 0.5555. Okay, now we want to write these in sigma notation. So we have our sigma notation, and we've got I equals, and I'm going to start at 0 and go to 0, 1, 2, 3, 4, 5, 6 to 6. Okay, and let's see. I see I'm counting by threes, so I'm going to use 3i. And let's see what happens. So I've got 3 times 1. That's going to give me 3. Oh, I'm sorry, 3 times 0. So that's going to give me 3 times 0, which is, of course, 0. Well, that's not what my first term is. It's 1. Well, if I add 1, that gives me my first term. Let's try the next one. 3 times 1 plus 3 plus 1 equals 4. Okay, so it looks like 3i plus 1 is going to be what I'm going to use. Let's try one more. So that's 3 times 2 is 6 plus 1 equals 7. And that seems to work. So there is my summation notation for that sum. Okay, let's look at the bottom. Let's look at the next one. We have a summation. And we're going all the way out to, and if we see we're plussing 1, 2, 3, 4, all the way out to 20. So that means my I is going from 1 to 20. And let's see. The numerator does not change, so my numerator has to be 3. And it seems to be 1 plus my I. So I can double check that. That's going to be 3 over 1 plus 1. That's good. 3 over 1 plus 2. That's good. 3 plus 1. 3 over 1 plus 3. That's good. So that looks like my summation notation for that problem. Okay, that does it for Chapter 9, Section 1.